we've studied two types of first-order differential equation. Those that were separable in 15.2 and those that were linear in 15.3. I suggested to you before, pardon me, there are many other ways to solve first-order differential equations, but the vast majority of applications seem to involve these two types of differential equations. So I'm not going to talk to you about any other techniques. There are lots of others, such as exact differential equations, integrating factors that make them exact, homogeneous equations, Bernoulli equations, Riccati equations, and others as well. So if you get involved in an application somehow in engineering that requires a different technique, then you just go and look that particular technique up. What I want to talk about today is in section 15.4. It is second-order equations that are reducible to a pair of first-order equations. Second-order equations in general are notoriously difficult to solve, unless they happen to be linear, and we'll talk about what that means in the next video. Generally, if I've got a differential equation for y as a function of x, and it's second order, it's likely to involve x's, y's, y primes, and y double primes. And we can denote that generically by saying it would look like that. It doesn't say anything, it simply says those are the things that would appear in it. The only one that's necessary, right, is to be second order. That one has to be there. These all might be there, or some of them could be missing. Those would be special ones. We want to talk about two special ones today. Type 1. Dependent variable y is missing. So when you look at the differential equation, all you see then are x's, y primes, and y double primes in it. You don't see y all by itself, right? So those two, or that kind of differential equation, can be reduced to a pair of first-order equations, and we do have some experience in solving first-order equations. So the technique is to do the following. So if you see this situation, excuse me, let v be equal to dy dx, or y prime, and dv dx to be equal to d squared y dx squared, or y double prime. If you did that, then the x's are still there, the y prime has been replaced by v, and the y double prime has been replaced by v prime. And so what have you got? A first-order differential equation to solve for v. So if you solve this differential equation and get the v, you put that v here, and you say, now I integrate, and I get y. So that's the technique. Example. I'll do one example of this type, then I'll show the other kind, which is going to be type 2, where the independent variable is missing, and I'll do an example of that, and then I'll do a third example, which falls into both situations, and kind of compare which one is easier. So here's this first example. That y double primed minus 2y primed is equal to x. So you can see that it indeed falls into this category. You see the y double prime, you have to. You see some x, but you don't have to. You see some y primes, but you don't have to. But here, no y's by themselves. So it's falling into this category. So if we make these substitutions, in for the y double prime, we put dv dx. In for the y prime, we put v, and the x dy by itself. So now we're down to solving a first-order differential equation for v as a function of x. And we ask, is it of the type that we're familiar with? Well, we're familiar with two types, separable and linear first order. Is it separable? No. Is it linear first order? Yes. Well, that's true, and it's in the requisite form, so we can say an integrating factor is e to the integral, whatever sits in front of the v, minus 2 dx, which is e to the minus 2x. What did that mean? It means if we take and we multiply all terms in this differential equation by this integrating factor, then the left-hand side is going to be the derivative of a product, and then we can proceed. So let's do that. Write e to the minus 2x dv dx minus 2 e to the minus 2x v is equal to x e to the minus 2x. And we know that the left-hand side has to be the derivative of a product. And this one tells you what the product is. It tells you that it's got to be v e to the minus 2x. But remember what I said to you the other day. I said, you check that you haven't made a mistake here by saying, this one times derivative is that one, now this one times derivative of that one must be that. Is this times the derivative of that, that? And the answer is yes. So you checked your integrating factor. Now we'll integrate. With respect to x. Left-hand side simply kills off the derivative. Integral x e to the minus 2x dx. Integrate that first here, we would use parts, right? You would put this one equal to the u and this one equal to the dv, but be careful, this dv is nothing to do with that v there. This is simply an integration by parts off to the side. So what does it say? Integration by parts is, then the du will be equal to dx, and the v will be equal to e to the minus 2x over minus 2. So substitute, it says u, v. U is this, v, that. Minus the integral of v e to the minus 2x over minus 2 du, which is dx. And so finally then, minus x over 2 e to the minus 2x. And if we integrate this, cancel, cancel, minus 1 over 4 e to the minus 2x. And now my constant of integration. So if we now multiply both sides by e to the 2x, we'll have that v is equal to minus x over 2, minus 1 over 4, plus c e to the 2x. And what's v? That's dy dx. So dy dx is equal to this. And in fact, if you remember, I said that you're replacing this second order differential equations with two first order equations. There was the first order differential equation. This is a differential equation. That's our second one, right? But it's rather trivial. Somebody says that the derivative of y is this, then go integrate. So y of x is equal to minus x squared over 4 minus x over 4 plus c over 2 e to the 2x plus d should be our final answer. You can, if you want, say, call this big E if you like, since it's just arbitrary constant. So there's that one. There is how we solve then if the dependent variable is missing. Reduces again. Making these substitutions gets you two first order equations. This one in this example, followed by this one over here, which will always be like this, and simply says integrated to find the y. So there's our first type. Second type. This time, the independent variable is x is missing. So generically, what you're going to see then is some y's, some y primes, some y double primes, but you will see no x's. Right? A Again, you might not see y's, and that's going to be my third example, that all you'll see are these two. You might not see this one, but you have to see that one. You start out the same way. You say, let v be equal to dy dx. And you say, and therefore d squared y dx squared is equal to dv dx. You might say, let's try the same thing. Well, watch what would happen if you did that. In for the y, it's going to be there. Right? So if we looked at it, you're going to say, there's the y. In for the y prime, I'm going to put v. And in for there, I'm going to put dv dx is equal to 0. And for the y double prime, I put this. And you look at it and you say, wonderful. It's kind of a bit of a problem. How many variables do you have in here? Y and v and x. But you want to use a differential equation in somebody, but you haven't got it. You've got too many variables. So doing this doesn't work. What we're going to do is the following. Do you agree that this is true? And I simply said, oh, dv dx is equal to this. And the answer is yes. Remember, first year, you can regard this as a quotient. Those dy's cancel. So that's acceptable. Well, what was dy dx? That was v. So suppose, instead of putting that thing in, I put this thing in instead. And what we'll be looking at? F, the y's are there. What's the y prime? That's the v. And you're going to put this in for the y double prime, v dv dy. So there's what's going to be in your equation. Y's and v's and more v's and dv dy. Two variables. V's and y's. But notice the drastic change. Ultimately, what you're searching for is y as a function of x. That's the objective. Find y as a function of x that satisfies this differential equation. And you look at here, what you're now going to be looking at is v as a function of y. Y has changed his role temporarily from a dependent variable here. In here, he's now the independent variable. You'll be solving this for v as a function of y. If you get it and you put it back here, v now as a function of y, you'll be looking at this differential equation later, which is now separable. And you can separate and finish. So let's see an example of that. Example 2. Y double prime plus 4y is equal to 0. Now, this example has two purposes. One, to show you that this technique will work. Two, to illustrate that there are sometimes better ways to solve a problem than you might first think about. Right? This method here is going to be the hardest way to solve this problem. We will solve it later because it's a special kind of differential equation called linear. And we're going to deal with linear second order and higher order shortly. Thirdly, I can look at this differential equation. I can see the answer. If you think about it, you're talking about y double prime being equal to minus 4y. Functions, so that when you differentiate them twice, you get minus 4 times what you started with. If you think about it, you can tell me what the answer is. Functions, I differentiate them twice, I get minus what I started with. That's what sine and cosine do. Differentiate sine twice, you get minus sine. You differentiate cosine twice, you get minus cosine. All you need to do is somehow incorporate the 4. Well, how about cosine 2x? If I differentiate that, will I get minus 4 times it? Answer yes. If I were to put a constant there, would it still do it? Yes. If I put sine 2x and differentiate that, do I get minus 4 times that? Yes. If I put a constant here, does it still do it? Yes. If I put a plus sign here, does it still do it? Yes. Okay. There is solutions. Done because you're clever at differentiation. Let's show that this technique will get you the same answer with much more difficulty, and then we'll deal with this guy again later as an in-between. Harder than this, but definitely easier than this. Right? So the technique says, let v be equal to dy dx, and let d squared y dx squared be equal to v dv dy. That's what it says to try and do. So what do we get? We get v dv dy plus 4y is equal to 0. In first order, remember both techniques, both types are supposed to reduce you from a second order equation down to 2 first order ones. So this is our first order one. We want to solve it for v as a function of y. So you're going to ask, is it linear? Is it separable? Is it linear? The answer is no. Right? You can say to be linear, I'd have to be able to write it in the form dv dy plus function of y times v is equal to function of y. That would be linear for v as a function of y, and this one is, because you get rid of that v there, it's going to go in the denominator, and but it is separable. We could write that v dv is equal to minus 4y dy. Right? I've separated it. And therefore we could say a one parameter family of solutions is defined implicitly by writing that the integral of v dv is equal to the integral minus 4y dy. This side, v squared over 2 is equal to minus 2y squared plus c. We want them explicit. We want to get v as a function of y, so we can put it here and solve. So I need to solve this for v. V is equal to plus or minus the square root of 2c minus 4y squared. Up with the 2 and take square roots. There then are explicit solutions of that differential equation. And what are we going to do? We're going to put this equal to dy dx. Because that's what v was, dy dx. So we will have, let's leave that there because that was what we're expecting. Dy dx is equal to plus or minus the square root of 2c minus 4y squared. Want to solve this now for y as a function of x. It's separable. Dy over the square root of 2c 4y squared plus or minus dx. And therefore, a parameter family of solutions. Notice I left out, I didn't want to write a one parameter because there's already a parameter here. I could have written a two parameter family of solutions because when I do this one, I'm going to get another constant, so we'll have C's and D's. So two parameter family would be okay. Solutions is defined implicitly by writing that the integral of dy over the square root of 2c minus 4y squared is equal to plus or minus x So all I have to do is do that integration on the left, and hopefully, I'm going to get this. Sure doesn't look like it at the moment, but let's proceed. Integration on the left. How are we going to find an antiderivative of this thing? Now notice something. C. Could C be 0? Well, if it is, then you're going to be integrating that, which is a bit of a problem. And if C is negative, it's just as bad. So the answer is, can C be negative or 0? The answer is no. If you were to look way back here, that one is telling you, if you take that one over onto this side, then that one will be positive, this one will be positive, and C therefore is positive. So there is no problem here with the C guy. I'm going to take this off. We'll remember that. So how do we integrate this? First here again. In solving differential equations of 15.2, 15.3, and 15.4 here, you've got to know all the techniques of integration you've done in first year. We've seen simple substitutions already. We saw integration by parts earlier today. You saw partial fractions last day. Today we're going to see trig sum. We solved this with a trig substitution. Let y be equal to. Remember how we did that first year? You think of, forget that, you think of 1 minus y squared. 1 minus y squared makes me think of trig identity, 1 minus sine squared, so immediately goes sine theta. But the objective is to get this to collapse. I need what sits here to be the same as what sits there. All right. What are you going to have to put? I guess we're going to need a c here, but we're going to have to put a square root, so when we square this, we get that c. On the bottom, let's see. On the bottom, I want to get a 2, and I got a 4. How about a root 2 there? If I square this now and put it here, am I going to see dy over the square root of 2c minus 2c sine squared theta? Is that what you're going to see? All right, so we take this, we square it, we get c over 2 sine squared theta, we multiply by 4, and we get, in dd, that's what we get. We need the dy. dy d theta is equal to root c over root 2 cos theta d theta. So on the top end, root c root 2 cos theta d theta is equal to that plus or minus x plus d. So what do we get? If we pull out, let's write then, we've got the integral root c root 2 cosine theta. We've got the d theta on the bottom. If we factor out the 2c, we get the square root of 2c, and we'd have 1 minus sine squared, which is cos squared, and the square root of cos squared is cosine. So we're down to that. Is equal to plus or minus x plus d. Canceling the cosines, cancel the root c's, and do we get them 1/2? Root c's cancel and the roots combine. And integrating theta equals plus or minus x plus d. Put back for theta. What is theta equal to from here? 1/2. Theta is equal to the inverse sine of root 2 y over root c. Plus is equal to plus or minus x plus d. We're getting there. Now the objective, solve for what? Up with the 2. Up with the 2, and then take signs of both sides. We'd have root 2y over root c is equal to the sine of 2d plus or minus 2x. How does that look? Last thing to do, solve for y is equal to, y of x is equal to root c, root 2. If you don't mind, I would like to expand this into sine 2d cosine 2x plus or minus, where'd that 2 come? No 2. We're expanding this. Sine of him, cos of him, plus or minus cos of him, sine of 2x. Beginning to look pretty good. Right? Beginning there. What is this? A great big fat constant. What is this? Another great big fat constant. How will I call them? A cosine 2x plus b sine 2x. And lo and behold, that was the solution that we spotted at the beginning. You can see that was a laborious way to get the solution of the differential equation, but it did work. One last example, which is going to fall into both categories. So example 3. This one, y double prime is equal to 1 plus y prime double squared. And as you can see, both x is missing and y is missing. So both techniques are applicable. Which one will lead to the easier solution? One never knows. One tries one, and sometimes they both work easily. Sometimes one works much easier than the other. You simply have to try. So let's try doing first the fact that the y is missing, right? Since y missing, and that was a type 2, set v equal to dy dx, and recall d squared y, dx squared, was equal to v dv dy. So we put those in. We'll have v dv dy is equal to 1 plus v squared. Type, and we only have 2 types, fortunately. Linear first order, and that kills linear, and that kills linear, but it is indeed separable. We could write that v over 1 plus v squared dv is equal to dy. Down with you, up with you. Therefore, a 1 parameter family of solutions is defined implicitly by writing that the integral of v, 1 plus v squared dv, is equal to integral dy plus c. If we do this one, that's a logarithm. The logarithm, I guess I don't need absolute values because clearly that's always positive, is equal to y plus c. How does that look? Right? Need to solve it for v. So that we can do our second differential equation. So let's see. Okay, up with the 2 and exponentiate. 1 plus v squared is equal to e to the 2y plus 2c. We could write this as d because that's e to the 2y times e to the 2c, call that d. Now solve for v. V is equal to, over with the 1 and square roots, plus or minus the square root of d e to the 2y minus 1. How does that look? What was v? dy dx. So dy dx is plus or minus d e to the 2y minus 1. Separates dy over the square root of d e to the 2y minus 1 is equal to plus or minus dx. And therefore, a two-parameter family of solutions is defined implicitly by right at the integral dy over the square root of d e to the 2y minus 1 is equal to plus or minus x plus e, new constant integration. So last step to do this integral. How are we going to integrate this thing? Back to 1710 again. Well, since we got this square root, it looks like it's another tricky sum. Notice again, if d were 0, you'd have a problem. If d were negative, you'd have a problem. But if you go back, this was the d. That's the thing I call d. And there's no way it can be 0, and there's no way it can be negative, so everything is just fine. But how do we integrate that one? Well, if I gave you the integral of 1 over the square root of y squared minus 1, what would you have substituted in first year? That's a tricky sum, right? And don't say, I'm going to put u equal to y squared minus 1, or I'm going to put u equal to the square root of y squared minus 1. You can try them, they won't work. This has got to be a tricky sum. And which one does it remind me of? Tricky sum minus 1, that reminds me of sec squared minus 1. So that means I'm doing a sec substitution. Let e to the 2y be equal to, no, I'm not going to go e to the 2y, I'm going to go e to the y. So I want that thing to turn into sec squared minus 1. So I'm going to put a sec here. If I did that, then that would be d sec squared. I don't want the d, so how do I put here a 1 over a square root of d? Is that going to do it? Pick that out, square it, or to get e to the 2y, and then multiply by d. That looks right. All right. So we do that, then e to dy dy is equal to 1 over the square root of d, the root of sec 10. Sec theta, tan theta, d theta. Or dy is equal to 1 over root d. I take this over, and what, e to the y? That's that thing. So we got sec theta, tan theta, d theta, and e to the y, put that in the bottom, 1 over root d secant of theta. So we're going to get, all right, we substitute those, we got on the other side, e plus or minus x is equal to integral 1. So, okay, let's write 1 over the square root of, we said we made that substitution in order to hear it again, sec squared minus 1. And sec squared minus 1 is tan squared, and the square root of tan squared is 10. So the bottom is collapsing to tan theta. We still have the dy, which is this 1 over, oh, those guys cancel. How nice. Then we've got, oh, those guys cancel, tan theta d theta. All right? Well, everything's canceled? Everything's canceled. Huh. Equals then theta plus e. Oh, we already have an e. Oh, it's already on the other side, I don't need it again. So that's theta. And what's theta? Theta I have to get from here is equal to the inverse secant of root d e to the y. So we've got that one equal to that one. Let's take secants. Then root d e to the y is equal to the secant of e plus or minus x. Take over the root d. And finally, take logarithms. Y is equal to the logarithm of 1 over root d, the secant of e plus or minus x. Almost there. We could leave that, but notice the log of a product is the log of the first plus the log of the second. And the log of 1 over root d, that's a constant, so how do we write g plus the logarithm of the secant of e plus or minus x? And say, finally, there's the answer. Not a simple task, right? We had to separate twice. We had inverse, we have logarithms, we have trig substitutions. So there's that. We said we would try it with the other substitution because not only was the y missing, or that was, oh, I think I screwed that up, right? I began this by saying, since y is missing, I tried that substitution, and that was a substitution if x is missing. All right, so change that, okay? Back to where I said, since y is missing, right? Now let's do, since y is missing. We'll set v equal to dy dx, and d squared y dx squared equal to dv dx. Remember the differential equation was y double prime, 1 plus y prime squared. So if we do that, then we'll have dv dx is equal to 1 plus v squared. We'll separate it. 1 over 1 plus v squared. dv is equal to dx. We can say a one parameter family. Of solutions is defined implicitly by integral 1 over 1 plus v squared dv is equal to integral dx inverse tan of v is equal to x plus c. V is equal to the tangent of x plus c. But what's v dy dx? Oh, this method seems to be a lot easier than the previous method for this particular problem. So now we got dy dx is equal to tan x plus c. All we have to do is integrate, and we're done. There's the final answer down there. Let's see if they look the same. So therefore, yx is equal to the integral of the tangent of x plus c dx plus d. Antiderivative of tan, first year. What is the antiderivative of tan x? Tan x. Call that arrow tan x. Was it not the logarithm of the absolute value of the secant of x? Is that not what it was in first year? Or was it cosine? Let's differentiate that. If you differentiate that, you get 1 over sec. And the derivative of sec is sec tan. Oh, that's right. So what's right? Secant is can. Right. So what's this one then? The logarithm of the absolute value of the secant of x plus c plus d. Is that what we got down there? Well, they look almost the same. These look very close. Those are the same. We got logarithms. This one's got absolute values. This has got plus or minuses. So they almost look the same, but not quite. Well, let's take a look. See if we can show that these two guys are the same. Correct? Let's take a look. Since this one's got two cases, maybe we could take the two cases here, right? I don't know where I came from anymore. All right. So let's take this one over here. Say, for positive sign, what are we looking at? Y of x is equal to g plus the logarithm of the secant of e plus x. That. That's looking very close to this. The only thing that's missing is the absolute values, right? What about the absolute values? What about them? Since I erased the other solution, we have it hard now to say that this guy had to be positive. So let's leave that part and simply say these kind of look the same. What about the negative? We have y of x is equal to g plus the logarithm of the secant of e minus x. We would have that one. So we choose the minus sign here, we have that. So all right, we want to say, is that the same as this? Would you allow me to put into here x minus e? Is that the same thing? Is the secant of something the same as the secant of the negative of that something? That's true, it is, right? Secant of minus theta is the same as secant theta, because it's a cosine. Cos of minus theta is the same as cos theta. Turn upside down. Yes! I can do that. Well, what's this? Minus e? Ha! I'll call that g. C. Not the same as this now? The answer is yes, it is. All right? So we could write this one instead of this plus or minus. They're the same. So there's an example done both ways. Which way was easier? Certainly the second, because they didn't have to make any substitutions whatsoever. Again, these are special second order ones. Either the dependent variable is missing or the independent variable is missing. That's not true. Right? If you were to simply say, hey, I'm going to put a y here, and I'm going to put an x here, now nobody's missing, that would turn out to be extremely difficult to solve. So that finishes that particular section. Next day we'll start talking about what our linear differential equation, and they will occupy the rest of this topic. See you next day.